Welcome back. This is the third part of the screencast on 13.6. This part is going to be quite technical, so good luck to all. Example 1, find the direction of steepest ascent of the function given here at the point 1, 2 and the maximum value of the directional derivative at that point. Here are two graphs that represent the function. When you zoom in a little, it looks like that. When you zoom out and from a different angle, it looks like this. Here you have the point 1, 2, so we can already guess that the maximum value of the directional derivative, which is the magnitude of the gradient, is going to be quite high. It seems to be very steep. So to find the gradient, we need the two partial derivatives, fx equals y over x plus y squared, and fy equals ln of x plus 2xy. Therefore, the gradient of f is this vector here, and at the point 1, 2, it means del f equals 2 plus 4i plus 0 plus 4j, and it's equal to 6i plus 4j. This is our horizontal vector that points in the direction of steepest slope, and if we want to know how steep it is, we need to find the magnitude of the vector 6, 4, and that is root 52. So the slope of the tangent plane is a little bit more than root 52 in that direction. Example 2. The temperature in degrees Celsius on the surface of a metal plate is given by the function t, where x and y are measured in centimeters. In what direction from 2, -3 does the temperature increase most rapidly? And what is the rate of increase? So let me just leave this and look at the graph a little. This is the graph of the function t. T equals 20 minus 4x squared minus y squared. So it looks like a 3D graph, but in reality, in the context of the problem, we have a flat metal plate, and the third dimension, the third coordinate, gives us the temperature of this flat metal plate. So in the center of the plate, it seems like the temperature is warmer. In fact, it's easy to figure out that at x equals 0, y equals 0, the temperature is 20. But if the further you go away from the center, 0, 0, the cooler the metal plate is. So if we wanted to actually visualize this metal plate a little bit better, by the way, this is the point 2, -3, we may want to look at this graph from above, something like that. And the point 2, -3 is barely visible down here. I sketched also the level curves so we can see where the temperature is equal to a certain value. Better than this graph, though, in 3D, we can look at this one here. It's the same, we have level curves, but this is much more visually explicit. This is our metal plate. We are studying the point here, and we are wondering in what direction would the temperature increase fastest. I'm going to show you. It's going to be in this direction, so perpendicularly to the level curve. This is not the gradient. In fact, as we'll see later, the gradient is a vector that is much longer than that, but it points in the right direction. So back to the exercise. If we want to find the steepest increase, we need to calculate the gradient of the function t. Del t equals partial derivative of t with respect to x times I plus the partial derivative of t with respect to y times vector j. That's easy to calculate. We find that it's equal to -8xi minus 2yj. At the point 2, -3, we find that the gradient is negative 16I plus 6j. What is the rate of increase at that point? We want to find the magnitude of that vector del t. 16 squared plus 6 squared, square root 17 degrees Celsius per centimeter, approximately at that point. A heat-seeking particle is located at the same point 2, -3 on the same metal plate. Find the path of the particle as it continuously moves in the direction of maximum temperature increase. So we are starting somewhere, and the particle is moving. It's always moving in the direction of increasing, highest increase in temperature. So it will follow a certain curve, and eventually it will reach the hottest point on the metal plate. How can we solve this problem? So we're going to call the position function of the particle r of t. And r of t is equal to x of t times I plus y of t times j. And our goal is to find x of t and y of t. Now what we know about this path, it is that it's always going to be following the highest increase in temperature. So the derivative of r of t is going to be parallel to the gradient at all times. R prime of t is parallel to the gradient, which we calculated in the previous example. We can write this like that: k times r prime of t equals del t. And if I look at it for each component, it means that k times x prime of t has to be equal to negative 8x, and then k times y prime of t will have to be equal to negative 2y. Now, r prime of t is parallel to del t. This is why we add a constant k. In fact, since we are not going to be caring about how fast this heat particle is moving, we could just say that r prime of t is equal to del t. That would work as well. But we'll keep this constant k here because we may find out in the end that there's a better choice for k than k equal 1. So we have two differential equations here: k times dx dt equals negative 8x, and k times dy dt equals negative 2y. The most obvious way to solve these two equations is just to take them separately, and we'll do that afterwards. But first, we'll use another idea, and here's what it is. If I separate the variables, negative 1 over 8x dx equals 1 over k dt, negative 1 over 2y dy equals 1 over k dt. If you notice, I can actually substitute 1 over k dt, and I would be rid of the k and the t. So that's actually a better idea. We'll start with that. Later on, we'll do it by solving each of these two differential equations separately, and it's going to be interesting as well. So now that I substitute, I will get negative 1 over 8x dx equals negative 1 over 2y dy. Here you are. The variables are already separated, so we can integrate right away. Oh, I changed the sign, and then I integrate 1 over 8 ln of x plus c equals 1 over 2 ln of y, and from here it's just standard algebra. I multiply everything by 8, and instead of writing 8c, I decided to just give a new name to that constant 8c, and now it's called k. ln of x plus k equals ln of y to the power of 4 using properties of logs, and e to the ln of x plus k equals y power 4. Here again, I can rewrite e power k as a new constant c. It's something you can do, or you don't have to, but it can make the equation a little bit easier to read. At this point, we're going to use the initial value, We know that the heat particle starts at the point 2, -3, so x equals 2, y equals -3, and we find that the value of c is 81/2. Therefore, if I substitute this value in the equation above, I find x equals 2/81 times y to the power of 4. This is the position function of this heat-seeking particle. So this is all you need to write. I'll do this problem a second time, this time solving each differential equation twice, each differential equation separately, but you don't have to copy that if you don't want to. This is where we were, where we chose to substitute. If we don't substitute 1/k dt, we work on the first differential equation. I'm integrating this and I find -1/8 ln of x equals 1/k times t plus c1. I'm starting to run out of ideas for names of constants. We have an initial value as well at the beginning when t equals 0, x is equal to 2, and that allows me to find the value of c1. So I substitute the value of c1 in the equation, and from here, again, just standard algebra, I'm trying to solve for x. I multiply by -8, and I find x equals e to the power of -8k times t plus ln of 2, which is x equals 2 times e to the -8/k times t. In exactly the same way, I can solve for y, and I can find that y equals -3 e to the -2k times t. One little difference between these two differential equations: when I get to ln of absolute value of y, we have to be careful. Since we know that y is equal to -3, I made a little mistake here, y equals -3, it means that y is actually equal to negative e to the power of -2k t plus ln of 3. In the end, we find y equals -3 e to the -2k t. So this is the same curve as we defined earlier, but this time it is in parametric form. We still haven't chosen k. We said earlier that we could choose k equals 1 right from the start. Now we can decide that we want to choose k equals -2 maybe, and therefore these are the parametric equations. What does it look like when we graph them like this? And of course, this is the entire graph. In our case, the particle is starting here and ending at the origin. So if we just jump back to the graph, we can see that it is always perpendicular to the level curves, and this particle will move like that until it reaches the origin, which is the hottest point on the metal plate. Okay, so that's it for this part of the screencast. You can do the textbook exercises 65, 67, and 69 if you want to practice what we just saw now, and then move on to the fourth and last part of this screencast. Thank you very much.